So today we're going to talk about how to interpret a position time graph or a velocity time graph and describe the motion of an object making that graph. Let's look at this first example. When we're trying to describe the motion of an object, we want to make sure that we always think about its initial position, whether it's speeding up or slowing down, whether it's moving at a constant velocity, and also which direction it's moving, whether it's moving forward or backwards. Now, each of these graphs, position time and velocity time, will tell us that in different ways. So let's look at the position time graph first. If we were to have an object that had a position time graph that looked like this, I know that the slope of a position time graph tells me the velocity. So when I look at the initial position, when time is 0, I see that the slope here is very flat. Almost 0. So 0 slope means 0 velocity. So it's stopped at the beginning. It has an initial position that's far away from 0. It's stopped. And then it starts to move in the positive direction, because I can see here the slope is always positive. No matter where I look, the slope is always going to be positive. But looking maybe halfway through, I notice that the slope is positive, but it's much steeper than the 0 slope before. So slope is positive and steep, which means my velocity is positive and fast. Looking at the very end, I notice that the slope is even steeper than it was before. So it's the steepest positive slope, which means the fastest velocity. So now let's take a look at what that might look like. As you can see, our object did have a slope. It started at 0, it got steeper, and then ended as steep as it possibly could. Now we show that on the velocity time graph because the value is very close to 0 at the beginning, and the velocity value continued to get more and more positive as time went on. Looking at an object like this, we'll do the same thing as we did before. So looking at a position time graph, I know that the slope tells me about the velocity. I can see that the initial position is not 0, and it's in the positive side of 0. So if I want to talk about the speed of the object and how fast it's moving and whether it's speeding up or slowing down, I can see that the entire time the slope is positive, so it must be moving in the positive direction. Because it's nonlinear, I know it must be speeding up or slowing down because it can't be moving at a constant velocity if the slope is not constant. So let's look at the slope at the beginning. Looking at this point, the slope is positive and steep. Because the slope is positive, that must mean the velocity at the time 0 is positive, and because it's steep, that must mean the velocity is large. Looking halfway through, I can see that the slope is still positive like we expected, but it's less steep than it was before. That must mean that my velocity is still positive, but less steep means that it must be smaller than it was before, so it must be slower. Finally, at the very end, it looks like a slope of 0. That means that my velocity is also 0. So we should see an object that has a very large velocity moving in the positive direction, and then it should slow down to a stop at the very end. Again, our position time graph does match. So we can see that we had a slope that started off steep and continued to get less steep as time went on. Now we showed that on the velocity time graph because here we had a velocity that was large and positive, a velocity that was still positive but less large, a velocity that was smaller and still positive, and then we ended at a velocity of 0. Looking at a position time graph like this, we're going to look at the slope to tell us about the velocity. We can see from the initial position that we start away from 0 in the positive direction. However, the slope here the entire time is negative. So if the slope is always negative, that means we must be moving in the negative direction the entire time. Looking at the first point, I see that the slope is negative and very steep. That means that my velocity must be negative and also very fast. Looking as we go on, my slope is still negative here at a point halfway through, like we would expect, except it's less steep than it was before. So my velocity must be negative and slower. Finally, at the very end, our slope looks very close to 0. So our velocity should look like 0. So the object should be moving in the negative direction, should start moving very fast, should slow down, and then come to a stop at the end of its motion. Let's take a look. Notice again our graphs match. Right, we have a negative slope that's steep, and it continues to get less steep as time goes on, but always in the negative direction. Now if I were to look at my velocity time graph, it would start with a velocity that was negative and large, and continue to approach zero because those negative values would be getting smaller and smaller. You should see how each of these points match up with the slope above in the position time graph. So let's look at this last position time graph. So seeing this position time graph, I see that the slope is still negative always, so we should be moving in the negative direction. Looking at our first point, we start far away from zero, so I can tell you that the slope is zero. If my slope is zero, the slope of a position time graph tells me velocity, so my velocity must also be zero, which means I'm stopped. As time continues, we see a slope that's not zero, so the slope is negative and steep. That tells us our velocity must be negative and fast. Looking at the last point, our slope is negative and steeper than the rest of the other points. So the slope, that must mean our velocity is negative and faster. So we're looking for an object that's moving in the negative direction with a velocity of zero. So it starts stopped, then begins to speed up in the negative direction and continue to speed up until it reaches its fastest speed. So let's see if we can match that. And we did. So our slope started flat and it continued to get steeper as time went on. So we should look for velocity points, y values that are zero at the beginning and then become more and more negative as our slope becomes more and more negative. So now we're looking at a velocity time graph. So instead of looking at the slope of a velocity time graph to tell me how fast I'm going to move, I need to look at the y values. So all of these points on the y value, how far away we are from the x-axis tells me how fast we're moving, and whether it's above or below the x-axis tells me if we're moving in the positive or negative direction. Now looking at this point, no matter what time I go to, it looks like the velocity values are always the same. They're always going to be whatever this value is. So that tells me, because it's a flat line, because it doesn't change, that our velocity must be constant. And because it's above the x-axis, we must be moving in the positive direction. If I were to make a position time graph prediction for what this object would look like with this velocity time graph, I need to think about what the y values tell me or what the velocities tell me on the velocity time graph and how I can interpret that as part of my position time graph. Because the velocity is always constant and it's always positive, the velocity tells me the slope of my position time graph, so the slope must be constant and positive. That's a positive slope. And constant means that it doesn't change, which makes it a linear graph. So something like this might be a good prediction. The slope is constant and it's also positive. Now you'll notice the velocity time graph doesn't give me information about initial position. So unless I'm told, I get to choose what my initial position will be. Looking at this graph, it could have been anywhere as long as my slope was positive and constant. It could have even been below zero. So a velocity time graph doesn't give me enough information to interpret the y-intercept on a position time graph. So notice here, while this may not be a perfect example, all of those velocities seem close to whatever this value is, which happens to be 0.5 meters per second. So now let's look at a velocity time graph like this. As we said before, we were looking at the slope of a position time graph to tell us about how fast we're moving and whether our velocity was changing or not. But looking at this graph, I'm not going to look at the slope, I'm looking at the y values. So at the very beginning, my y value is 0. So that tells me that my velocity is 0. So I must be stopped, I'm not moving. As time goes on, my y value gets further away from the x-axis. So it's positive and further from 0. That must mean that my velocity is also positive, and being further from 0 means that it's faster. Looking at our last point, the y value is positive and farthest from 0. So my velocity is going to be positive and fastest. If I had to make a prediction for what my position time graph would look like, I know that the velocity is going to start at 0, so I should have a slope that starts out very close to 0. Then at some time in the middle it should get steeper, and then it should be steepest at the end. So connecting that, I must have a nonlinear graph that curves up. Again, I get no information about initial position, so I can choose whatever I want unless I'm told otherwise. So taking a look at what happened, we did see an object that started with a slope of 0 on its position time graph and got progressively steeper as time went on, meaning that it got faster. We also see an object that starts at 0 and then begins to speed up as time goes on, which is shown by points that are getting further and further away from the x-axis. Because remember, the x-axis on a velocity time graph represents a velocity of 0. So the further away we get from the x-axis, the faster we're going. Looking at a velocity time graph like this, we're going to interpret the point. I see that at this point, I have a y value that's positive and large. That must mean my velocity is positive and fast. All of these other points are still positive, so when I look at them, the y value is positive. The only difference is that it's closer to the x-axis. So that means that my velocity is positive but slower. And at the very end, the y value is 0. So if I wanted to make a prediction for a position time graph that looked like this, we're going to start with a slope that's positive and steep because it was far away from 0. Halfway through, I'm going to have a positive slope that's less steep because it's closer to 0. And then at the end, I'm going to have a velocity that is very close to 0 or 0 itself. So we should get a curve that looks something like this. Now let's take a look at what we would get. Again, we see our slope starts out steep, gets less steep, and then comes to 0. And we show that on the velocity time graph by the distance away from the x-axis. So remember, the y values on our velocity time graph should tell us something about the slope on our position time graph. Looking at this velocity time graph, initially we start out with a y value of 0, which tells us that our velocity is 0. Sometime down the road, we see that our velocity is negative. We know that because it's below the x-axis. So our y value is negative and far from 0. That tells us our velocity is going to be negative and faster. Our last y value is farthest from 0 and still negative, which means our velocity is fastest and negative. So looking at this, we should see an object that starts at a velocity of 0, moves in the negative direction, and starts to speed up. So if I wanted to make a prediction for this position time graph, I would start with an object that has a slope of 0, and then has a slope that becomes more and more negative, but steeper. Because I don't know where I'm going to start, I'm going to choose to start my y-intercept up here, my initial position. I'm going to start with a slope of 0. I'm going to have a slope that gets more steep as time goes on, which would give me a position time graph that looks something like this. And that's exactly what we see. Slope starts at 0, becomes more and more negative as time goes on. Y values that start at 0 and get more and more negative as time goes on. Looking at this velocity time graph, I have a y value that's negative and very large, larger than all the rest. Tells me my velocity is going to be negative and large, so negative and fast. Sometime later, we're getting closer to the x-axis, so that means that my y value is closer to 0 and still negative. So my velocity must be negative and slower. Finally, we get to a y value of 0, which means we get a velocity of 0. So the y value is 0, that means that the velocity value must also be 0. So we're stopped. So looking at an object with this sort of velocity time graph, I would see that it starts at a velocity that was negative and fast, and then gets slower and slower because the y values are approaching 0, while still moving in the negative direction. So if I'm making a position time graph prediction, I should see an object that has a very, very steep slope that's negative at the beginning, and then a slope that gets less steep as time goes on until it flattens out to 0. A graph like this would look something along these lines. Looking back at our graph, we see here that our slope is negative and steep, and it gets less steep as time goes on. Likewise, the y values are large and negative and get less negative as time goes on, which means they get closer to 0. When making a prediction for this graph, things get a little bit trickier. You'll notice before in all of our other examples, either all of the velocity values were below 0 or above 0, meaning that it was always traveling in either all negative directions or all positive directions. But looking at this, we see here the y values are negative. That means that our velocity starts negative. while here we see y values are positive, which means our velocity must be positive. So that means at some point our velocity changes from negative to positive, and the negative and positive part of a velocity tells us which direction it's traveling. So this object must be turning around. Let's look at the points and see if we can interpret it that way. So initially we have a negative y value that's far from 0. So that must mean our velocity is negative and fast. As I keep going, I see that our y value is negative but closer to 0. This means our velocity is going to be negative but slower. Now, dead in the center, we have a y value of 0. So that means we must have stopped. After that, we see a y value that's positive but further from 0. So our velocity must be positive and faster. And then finally, we have a y value that's far from 0 and positive. So our velocity is fast in the positive direction. So looking at this, we should see an object that starts moving in the negative direction, moving quickly, but then slows down, stops, and then starts to speed up after it changes direction. So it slows down, stops, turns around, and then speeds up in the other direction until it starts moving very fast at the end. If I wanted to make a prediction for a position time graph, I need to choose an object that has a negative velocity that's steep. That negative velocity is going to get less steep until it flattens out to 0. Then after that, it must be a positive slope that gets steeper and steeper. You should get a graph that looks something like this. And when we run our trial, we see that we get just that. Large negative slope, smaller negative slope, a slope of 0, a positive slope that's somewhat large, and then a very steep positive slope, which we can see based on the points that we have here. Negative y value, less negative y value, 0, positive y value, and then a more positive y value, giving us our linear fit.